So I'd like to start by going over the Energy Skate Park Interactive Lab that you did last week with the substitute teacher. And I want to go through this and go over the answers so that way you can kind of check your answers. And I want to go over the concepts that are super important that I wanted you to get out of it. So let's take a look at the actual interactive. Um, so when you do this, one thing I wanted you guys to notice is that as the skater goes, um, you should notice that this total energy needs to stay the same. And the reason for that is you've always heard that energy cannot be created or destroyed. And this is the application of that. So my total energy has to stay the same. Um, and it doesn't matter what kind of energy I have, these need to add up together to equal my total amount of energy. And that total has to stay the same. Now, if I turn on friction and make it more real life, you'll notice that this thermal energy is getting bigger and bigger, and that's because of friction. So if you take your hands and you rub them together, and you start by rubbing them together slowly, and then you go faster and faster, and then rub them together and push hard, you'll notice that your hands get warm, and that's because of friction. And so that's what this thermal is it's kinetic energy. Because of friction, that kinetic energy is going from kinetic into thermal. And as it goes and you rub your hands back and forth, more and more of it is turning into thermal. The skater is going to have their energy turn into more and more thermal until they stop moving. So my velocity is 0, the height is 0, and now you'll notice that my thermal and total energy are the same. So the friction between the board and the wheels and the road or the bearings or whatever it is has gotten warmer um, with the same amount of energy as we started with. And that's that. So the other thing I want to talk about is how this applies to real life. Now, if you go down Cuesta Grade, which is a big mountain, and you start at the top of the mountain like this, you're already moving fast. Um, and here I am. Let's say I'm at the top of Cuesta Grade. I'm moving, so I have some amount of kinetic energy. And then at the bottom, I'm going to have I'm still going to be moving, but this potential energy here is going to have to convert into thermal in real life because I don't want to be going super fast at the bottom of a hill in my car. I need to be driving just a normal speed. And so this potential energy has to all go into thermal. And the way you do that is by applying the brakes on your car. So as you push the brakes on your car, two pieces of metal rub against each other. And it turns that kinetic energy of the two pieces moving relative to one another, and it turns it into thermal energy, which is why if you push your brakes the whole way down the big hill, by the time you get to the bottom, it's going to be stinky because it's really bad when your brakes get really hot. And the reason why they're getting hot is that energy is turning into thermal energy. The other way you can do it is you can also heat up your engine a little bit. And the way you do that is by shifting gears, and you can shift down so that instead of that kinetic energy turning into thermal in your brakes, it'll turn into thermal in the engine of your car. The difference being the engine of your car is designed to be really hot, whereas your brakes are not good with getting super hot. So then it's better for your car if you shift down and then you don't wear out your brakes or destroy them. All right, so now let's take a look at the worksheet. So here I want to talk about what kinds of energy we're going to see as the skater goes from A to B and B to C and from C to D. So as it goes from A to B or B to C, it is getting lower. And what you'll notice in this simulation is when our skater is up high, It has more potential energy. When it gets down to the bottom, this is when you're going to have more kinetic energy. And so in my simulation, I'm going to see that as this goes down the hill, my potential energy is going to decrease as it's going down, which will be from A to B and from B to C. My potential energy will increase as I go from C back up to D, and that's because my height is getting bigger again. In terms of my kinetic energy, it's going to increase as I go down the hill, which makes sense. The faster I go, the more kinetic energy I'm going to have. And then when I go back up the hill, I'm going to slow down, so my kinetic energy is going to decrease. Notice that for all three of these, your total energy is going to stay the same. The skater should have the most potential energy at the top of the ramp because that's where the height is the biggest, and gravitational potential energy is mass times g times your height. So the bigger the height is, the more energy you'll have. Where does the skater have the most kinetic energy? Well, that is going to be at the bottom of the hill because that's where you're going the fastest. And then how does mass of the skater affect the total amount of energy? Well, if I go here, and I drag this little mass thing smaller and bigger, you're going to notice a couple things. The total energy gets bigger over here. You're going to notice that in terms of my skater, the skater gets bigger or smaller, and the circle above the skater also gets bigger or smaller to represent how much energy there is. All right, the wavy ramp is exactly the same concepts. Here are the answers for those. So again, as you're going downhill, the potential energy decreases, kinetic energy is going to increase. So this is when you go down and up and down and up again. And so you'll notice decreasing, increasing, decreasing, increasing. The answers for these questions are exactly the same as the previous one. So it doesn't matter what shape the ramp is, the same thing is going to apply. And then I want to talk about this table. So originally when I made this, for some reason, I thought that this worksheet had numbers on the speedometer. And I did not realize that these don't actually have numbers. So the way you're going to do this one, whoops. So you take your skater and you're going to put them all the way at the top, all the way exactly at 6, and you'll let go. And then you need to click down here on slow motion. And then I'm going to let it get all the way up to 6 again. And then you will notice that my speed is a little bit above 0. So I'm not quite there. So you can take this and go, there we go. There it is slowing down. My skater switched directions. So this is my speed of 0. And then what I want to do is I am trying to fill in this table over here with this speed. So I need to start with the speeds. And if you are very specific and very careful, you can get a pretty good answer for this one. So if I go to 5, there it is. Now I'm exactly at 5. And then each one of these tick marks represents 1. So this is 0, 1, 2, 3. I would say that's 4.3 perhaps. So I would say that my velocity there is 4.3. So at 5 meters, it's at 4.3 meters per second-ish. And then to calculate my kinetic energy, this is going to be 1/2 times my mass, which is 20, that's given, times my velocity squared, which would be 4.3 squared. And then I just need to type that into a calculator. And so that gives me 184.9. Now, obviously, I'm not going to be super precise here because they're just this little speedometer thing. I can't read exactly what my speed is. Now, theoretically, my total energy will stay the same. Um, so the way you find potential energy is mass times g, which is 9.8, times the height, which for each one of these it changes. So these are all of my potential energies that I've calculated. And so then to get my total energy, I just have to add this together. So I have the 184.9 plus the 980, and I get 1164.9. All right, so it's not perfect, but it's pretty darn close. So considering that I have not super great um, precision with this simulation, I'm doing pretty well. All right, I'm going to go ahead and go to the next one. All right, that's about there. So this one's not going to be exactly perfect because I'm not exactly at a height of 4, but we're going to go with it anyways. So this is 0, 1, 2, 3, 4, 5, 6. We'll call it 6 point, I don't know, 6.2. So we'll go 6.2 meters per second. I'll plug that in here. All right, so I plug that 6.2 meters per second into my kinetic energy equation. I get a kinetic energy of 396.8. And then to find my total energy, I'm going to add these together. Perfect. All right, so this one I'm a little bit above, but overall pretty darn close. All right, so then I just keep repeating this process. Now, I know that this total energy is not going to be exactly perfect. That's okay. Also, if you've already done all of the kinetic energy stuff um, and you used different amounts for each of those tick marks, you're going to get a wildly different number. Your potential energies should be the same as mine here. And then your total energies will be different if your kinetic energies are different. So again, this is me just doing the best I can so you can kind of see how it works. And to get the idea where your kinetic plus your potential is going to be equal to your total. All right, and then in conclusion, you should notice that as the speed increases, your potential energy is going to decrease. And as the speed increases, your kinetic energy is going to increase. And as the speed increases, your total energy is going to stay the same. If you have any questions about this worksheet, let me know. Otherwise, thanks for watching.